Hello, here is your notes 3.1 for my honors algebra 2 course. So this normally I split this into a few different days, but since we want to start accelerating a little bit, I'm gonna kind of bunch this all into one. So notes 3.1, this section or this entire unit is all about systems of linear equations. So first off, I want to make sure you guys can identify. So we're just gonna kind of define it, let you guys know what it is. Um, Next off, we're going to solve systems three different ways. First way we're solving is by graphing. So it's just like it sounds. You're going to graph it basically to find your solutions. And the next two are actually algebraic approaches. First one is called substitution. The other one's called linear combination. Um, it's also known as elimination. So this section or this unit, this entire unit should be very familiar because you went over it in Algebra 1. Um, these last two are considered algebraic approaches. So this actually isn't anything new, so it should just be kind of like a refresher for most of you. Um, so just to kind of refresh even more, what's a system of linear equations? So first off, the word system usually means that it's a bunch of stuff grouped together. And linear equations, you should know what a linear equation is. We've been working with them for the last chapter. So system means system of linear equations just means it's basically more than one equation put together. Um, so that's what that is. Now, what does it mean to solve a system? So since we're working with linear equations, we're looking for solutions. Um, so think about one linear equation. One linear equation could be y equals 5x plus 1. So if you think of a solution to a single equation, that means that whatever, if you have an x value, then you can get out a y value, and that's considered a solution. So let's say x is a 3. What you would do is you plug in a 3, so you get y equals 5 times 3 plus a 1. So that's going to be a 15 plus a 1, so y equals 16. So one solution to this equation is 3 comma 16. Okay. Um, so what does it mean to have a solution of a system? So two of them at the same time. So if this point, since this point works in this equation, it's considered a solution. So in order for it to be a solution to a system, it has to, you'll have a second equation, so y equals blah, 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 blah. So not only should this work in here, it should work in another equation too. So that's what a solution to a system means. It means whatever your system is, you have, in our case, it'll be a point. You'll have one point that'll work in both equations. Um, so let's go over the first way. So graphing. Now we know we're doing linear equations, and we're going to graph them. So think back to when we graphed lines. So let's say this blue line represented one equation that we saw the equation and we graphed it, and it ended up looking like this. Okay? So keep in mind, the blue line is made up of a bunch of points, like as many points as you want to put on the line. It's actually infinite amount of points on this line. Every single one of these points represents a solution to whatever equation this came from. So every single one, as many as you can make on that line. Just think of it made up of a whole bunch of points, okay? So the blue line represents solutions to one equation. So the green line, we'll make this green line, could be anywhere, doesn't matter, as long as it's linear, because we're working with linear equations. So this green line, we'll say that green line represents, it doesn't have to go like that. It could look like this, could look like this, anything like that. So the green line, just like the blue line, represents a whole bunch of points. You can make as many as you want on this line. It's actually an infinite amount of points. So if the green line is made up of a whole bunch of points, which are a solution to the green line, which is one equation, and the blue line is made up of a whole bunch of points, which represent the solutions to another equation. The solution to both equations would be where they cross. So they cross right here. So that dot that I just made, that point, is on the blue line. So it is one of the solutions of the blue line. This is also one of the solutions on the green line because it's on the green line also. So since it's on the green and the blue line, it's the solution to both of those lines at the same time. So that would be the single solution to both equations, is where they cross. That's what you do when you're graphing, okay? So in just a real quick way of saying it, we're looking for where they cross. Yeah. Okay. There it goes. Okay, so solve by graphing. Um, both of these are in standard form. Your worksheet that I'm going to give you guys is going to have it in a whole bunch of weird forms. Your job is to first transform it into a form that is easy for you to graph. I don't care if you transform it into standard, slope intercept, point slope, whatever you guys want to do. Just transform it, and then you should be good. Okay. All right. So let's see here. This probably isn't the best one to use for graphing. Let me change this a little bit. Let's see here. Y equals, yeah, that's not going to become very nice. Let's change this number right here. Let's make that a 6. That's a better example. Okay, so solve that by graphing. Now, let's see here. This one right here, you could turn it into slope intercept form, or you can just graph directly from there, find the x and y intercepts. For your x-intercept, it'll end up being a 2x equals a 6, because I just changed it into a 6. You know what? Never mind. Sorry. Let's go ahead and do this just like this, because I think I put it like this for a reason. So x-intercept. Sorry. 2x equals 1. If you guys wrote that down already, yeah, just rewrite it. Intercept is negative 3y equals 1. So 2x equals 1, that's x equals 1/2. This is y equals negative 1/3. Okay, so that's your x and your y intercepts. So go ahead and graph that. I got mine on the next page. So hold on. Actually, I should probably make that bigger. Single page. Single page. Okay, so my x-intercept's at 1/2, my y-intercept's at negative 1/3. So x-intercept is at 1/2, which is about right here. Y-intercept is at negative 1/3. So negative 1/3 is about approximately right about there. All right. And now you just connect those with a nice neat line. And there you go. No, I don't need that to be anything. Okay. So that's one of our equations. That's all the solutions that work on there. So now we're going to do the other one. Same thing, standard form. So I'm going to make my x-intercept and y-intercept. X-intercept here will be x equals 3. This is all from last chapter, so you guys should already know how to do these. Y-intercept is y equals 3. So 3 and 3. So I'm going to make this in green. X-intercept's at 3. Y-intercept's at 1, 2, 3. Oh man, that's not going to be nice and neat. See, that's why I didn't like doing this one, but I'm going to do it anyways. So this actually is showing one of the big problems with graphing is that you have to be really accurate. So as you can see, mine's not that accurate because I can shift these around a little bit, but it's looking like they're crossing at about 2, not exactly 2, 1, but remember, it's not exact because these lines are kind of not very nice. These 2 points are approximations. They're not even really getting there. So that's one of the problems with graphing. But let's say this is our point, and that's approximate. So I'm going to say that's about at 2, 1. Now I know it's not quite on there, but that's more because the graph is a little bit sloppy. So think about 2, 1. If I put a 2 and a 1 in here, so we said that our solution is actually 2, 1. Now if I actually plug that in, 2 and 1, that equals a 3. put 2 and a 1 here. 2 times 2 is a 4, minus 3 times 1 is 3, that is 1. That actually works out. That is your solution. Okay, so that's how you solve by graphing. Now, the problem with graphing is if you have fractions like this, so actually that's the next slide. Why don't we like solving by graphing? The reason is because you have to be very accurate. And unless you have a bunch of nice graphing tools or a graphing calculator, you probably might be off by a little bit, just like I was right here. Especially if you have fractions that you're trying to estimate by. That's why we actually don't like doing by graphing unless we have some type of graphing tools or something like that. Okay. So yeah, so first graph them, figure out where they cross. Hopefully you guys get nice neat numbers where they'll cross at a nice neat place. Otherwise, just kind of estimate, plug it in, check, see if you get close to it or not. Okay. And special cases, there's a couple special cases here. Since we said that the solution is where they cross, what if you were graphing two lines and they were parallel? If you graph two lines and they end up being parallel, and we know that the answers are wherever they cross, parallel lines never cross. So that means that this has no solution. Okay, you have two lines that are parallel, so special case on that. So you're graphing one, then you graph another one, they end up looking something like this. They never ever cross. Now, just because you draw your lines weird and you draw like a line that looks like this, and you stop your line like that, that doesn't mean it never crosses, because your line might actually keep going. It does keep going and then eventually crosses. So you got to make sure they are parallel. And if you remember from last chapter, parallel means they have the same slope. Another special case that might happen here is if you actually have two equations that look different, but they end up being the same equation. They're actually equivalent equations. That means one's right on top of the other. Now, if you think about this situation, that means that the green line and the black line are on top of each other, meaning every single point that's on one is on the other one. What we call that in math is that it has an infinite amount of solutions, or infinite many solutions, because every single point is a solution because it works on both. So those might happen. So that's how you solve by graphing. Basically, graph both lines, figure out the point where they cross. That's your solution when you're graphing. Now, like I said, graphing is not the best way because if you get sloppy with your graphs, then basically you'll get the wrong answer. So the two methods that are more accurate are algebraic methods. We call them algebraic methods because you use algebra to solve them. First one's called substitution. You do exactly what it says. You're just substituting a whole bunch of times. The other one's called linear combination, also known as elimination. You call it elimination in Algebra 1. A lot of the higher classes call it, higher classes meaning like the pre-calc, calculus classes, things like that. We call it linear combinations because you're actually combining the lines together. So we'll go over substitution first. So what does it mean to solve by substitution? Now, you've actually done it before. We've done this when we were evaluating. So I used to give you guys equations like y equals 2 times x minus 3, and then I said, okay, what if x equals 1? What did you do with it? You basically said, okay, x is equal to 1, so I'm going to take this 1 and put it into the x spot because I know what x is. X is a 1, so it's going to go in this spot right here. That's actually combining because you combined, if you think about this top part, this is an equation, and this is a different equation. They're totally different equations. But since you know what one of them is equal to, you can start combining them together. So when we used to substitute, that's basically what we're still doing. So what I'm saying is y equals 2 times 1 minus a 3. So 2 minus a 3, which is a negative 1. So your answer here is 1 comma negative 1. If you were to graph these two, that's the point where they would actually cross. So if you were to graph this line and graph this line, they would cross at that point. Okay, but we're not graphing because if you get sloppy, you might miss that point. So that's basically what we're doing. You're taking one equation, substituting it into the other equation. Now there's a couple steps here because it does get more difficult than the one I just showed you. First step to solving by substitution is to pick one variable and isolate it in one of the equations. The one that I just showed you had x isolated, so you can just plug it right in for x. So first pick a variable and isolate it. Second step, substitute into the other equation and solve. So whatever variable you isolated in the first one, you're going to take that and then substitute it into the second equation or the other equation. Substitute. So after you solve that, you're going to get an answer. It's either going to say x equals or y equals, and then you're going to take that and substitute it into any of the other equations. But whatever you guys did for step 1, that's probably the easiest equation to substitute it in for. Solve for the remaining variable, and then you're done. So here's why I picked that one for example 1, because I want to do the exact same one. So we just did this one for example 1. This system is actually the same as example 2's system, but we're going to solve this in a different way. We're going to use substitution. Now looking at this, I don't have any letters by themselves. So what I'm going to do is I'm going to number these. I'm going to call this equation 1 and equation 2. That way you guys know which one I'm talking about. So I got to isolate a variable first. There's no variables isolated here. So first thing is, pick a variable that's easy to isolate. This x is not very easy. You got to get rid of the 3y, then you got to get rid of the 2. Same thing with this y right here. Second equation, both of these look like they're pretty easy to isolate. So pick either one of them. It doesn't really matter which one. I'm going to go ahead and pick x. So what I'm going to do is I'm going to take equation 2, and I'm going to isolate the x. So I'm going to subtract y. So x equals negative y plus a 3. Okay, so that's step 1. Step 1 was to isolate a variable. We did that. Now what we're going to do is we're going to take this x value. I know x is equal to negative y plus a 3. It's equal to all of this stuff. So now what I'm going to do is I'm going to take all of this stuff and then plug it into the x part of number 1. So to go over that again, we isolated in one of them. So the second equation, I isolated the x. Now that I know what x is, I'm going to plug it in for x right here. So just like before, if I said x equals a 6, you would have put a 6 right here. If I said x equals a 10, you would have put a 10 in for x. But x equals this entire group of stuff. So this whole group of stuff goes in for the x right here in the other equation. Don't plug it back into the same one you just worked with. That'll mess up. So you have to kind of put both of them in the mix. So you work with the second one and then plug it into the first one. If the first one you work with is if you work with the top equation first, then you'd plug in whatever you got right here into the second one. Okay, so you got to kind of mix them up like that. All right, so here we go. I'm going to take it, plug it in. So it'll say 2. I'm plugging in for my x minus a 3y equals a 1. Now the stuff that I'm plugging in for x is the negative y plus 3 stuff that I just found out. All right, so the next step is, now if you notice, now we only have one variable, so you can solve for that. So first off, just distribute. So you're going to get negative 2y plus a 6 minus a 3y equals a 1. Combine like terms, that's going to be a negative 5y plus 6 equals a 1. So you're going to subtract 6 now. So you're going to get negative 5y equals a negative 5. So y has to be a 1. In the end, remember, you're looking for a point that's on both of the lines. So we have our y value. Our y value is a 1. So now that you have your 1, you've used both equations. So you can actually take this one and plug it into either one of the original equations and get your x value. So you can either plug it in here or here. Or you could actually plug it into this part right here also, because if this one and this one are equivalent equations, we used properties of equations to get to there, so you can actually just plug it into here. That's probably the easiest one. But this one, or this one, you'd get the same thing any of the ways you plug it in. So I'm going to go ahead and plug it into the one that has x by itself already. So x equals negative y plus a 3, and then we figured out y was a 1. So this is going to be x equals 2. So 2, 1 is your answer. And if you remember, back over here, 2, 1 was our answer over here, so it looks like we did it right. Okay, just to show you too that you could actually plug it into wherever you want. If I would have taken this 1 and plugged it into here, you would have had x plus 1 equals 3, which means x is still a 2. If I would have took it and plugged it into here, negative 3 times 1 would have been a negative 3. And then if you solve that equation, you still get a 2. Okay, because you would get 2x minus 3 equals 1. And then solve that and you get x equals 2. So it doesn't matter where you plug it in. So if you forget to plug it in here, it's not really that big of a deal. So the last method is called linear combinations. In order to know where this comes from, you got to know what an equation actually means. Now, 5 equals 5 is obvious, 2 equals 2 is obvious. If I take this equation and combine it with this one, I should get an equation, a third equation, that's still true, because if you add, so if you remember, when you combine, um, basically, properties of equations say if you add something to one side, add it to the other side. So 2 is equal to the 2. So if I combine these two together, I get a 7 equals 7, which is still true. So I'll still get a true equation when I combine one equation with another equation. So steps to solving by linear combinations. All right, let's go through this. So first, if you need to multiply each equation so that you get one of the variable terms to be opposites. So either your x's should be opposites or your y's should be opposites, because what's going to happen is you're going to combine them and they're going to cancel. Once you get them to be opposite, combine the equations. One of your variables should now be canceled out. If they're not if you don't have one variable canceled out by the second step, then you did something wrong. Third, once you get done combining and canceling one, you're going to have one variable left. You're going to solve for that. You'll now have one variable solved for, and then you take that and plug it back in, substitute it back in into any of the equations from the original, and you should be good. Check your answer, make sure you did it right. Hey, look, same one that we just did a little while ago. So now what you should not do right now is if you draw a line under here and you try to combine right away, it's not going to work, because these do not cancel and these do not cancel. So we got to do a little bit of work here. Sometimes they will cancel. If they're exact opposites to start with, just cancel them out. So first off, just pick one of your values you want to cancel. So I'm going to say my x's. You could have done your y's, but I'm going to do my x's. I'm going to take this entire equation and multiply it by something so that I can make my x's cancel. Now my x on the top is a 2x. Opposite of a 2x is a negative 2x. So I'm going to multiply the entire bottom one by a negative 2x. Sorry, a negative 2. All right. Top one, ooh, that's the bell. Top one I'm just going to multiply by 1. So I'm going to get a 2x minus 3y equals a 1. The bottom one I just multiplied by a negative 2, so it's a negative 2x minus 2y equals a 3. Sometimes you got to multiply the top and the bottom to make them both opposites, but the whole goal is to make them opposite. All right, so now that I have opposites, now I can combine. So I'm going to draw my line. I'm going to combine these together. Those actually cancel out. A negative 3y and negative 2y, if I combine those, meaning combine like terms, I'm going to get a negative 5y equals, wait, something went wrong. Oh, this is a 6. Okay, not a 5. Negative 6. Sorry, wow, that was off. Negative 2 times 3 is negative 6, so that's going to be negative 5. So y equals 1. And remember, the whole point here is to get an x and a y. So y is a 1. Now what you're going to do is you're going to take that 1 and plug it back into one of the originals. Doesn't matter which one. I'm going to take it and plug it back into the bottom because that looks easier to work with. So x plus 1 equals a 3. So x equals a 2. So 2, 1 is your answer still, because we still had the same equation. All right. So that's how you approach that one. Couple special cases here. Sometimes you might end up with something like this. Say you had a 5x plus 7y equals a 1, and you had a 10x plus a 14y equals a 3. Okay? So if we're doing combinations, doesn't matter which one you guys are using. So I'd say multiply the top by a negative 2, because I'm looking at this 10x, and I know I can make a 5x into an opposite of a 10 by multiplying it by a negative 2. Oh, I was showing it over here. Normally I show my classes like this, draw an arrow, you're multiplying the top by a negative 2, multiplying the bottom by just a 1. That's negative 10x minus 14y equals a negative 2. 10x plus 14y equals a 3. So looking at this, these cancel and these cancel. You actually canceled everything on that side, and you got a 1 on that side. So the problem here is that your variables are gone. you can't solve for anything else because now you're all out of variables. This is a special case. Now, what you need to do is you need to look, because this might happen. If your x's and your y's both cancel, look at the statement that's left over. If it's false, because 0 is not equal to 1, if it's false, that means there's no solution. Now, if you did this and then say that you ended up with like all the variables canceled out, you ended up with a 7 equals a 7. That's a true statement. Now, so this would be no solution, is if the statement left over is false. If it's a true statement, this is called infinite solutions. You can just use the infinity sign. So graphically speaking, what this means is if you're going to graph these would be parallel lines. If you're going to graph the two equations that and this ended up happening with, it means that you had parallel lines that never crossed. That's why there was no solutions algebraically. Infinite solutions was the other case that I told you guys about, where it was actually meant that hold on. It actually meant that one line is right on top of the other line. Okay, that's what it means when it's a true statement. All right, so tomorrow you guys do have a worksheet and try to help each other out with it. Like I said, this should have been reviews, so you guys should have been over these process. You should have been over these methods before. Okay, try your best on it, and tomorrow work on the worksheet. Do not turn it in, and then Monday. Over the weekend, Friday, I'm gonna post another YouTube video going over another part, and then Monday will be a work day. We'll slow down a little bit just to make sure you guys understood those two parts. Actually, we'll spend the first half of the day seeing if you guys understood those two parts, and then probably do notes the second half of the period. Okay. All right. I'll see you guys on Monday. Take care. Bye bye.